Hello, so in this video we will talk about the Erlang 2 distribution and we will derive the PDF or the probability density function of this distribution by basic principles, which means that we will use our knowledge of finding the PDF of a summation of random variables, and we will use basic integration techniques in order to derive this PDF. So let's start with the definition here. So a random variable x is said to have an Erlang 2 distribution if it is a sum of two independent and identical exponential random variables. So in other words, we have y1 and y2 as exponential random variables where y is always non-negative. Then x is a Erlang 2 random variable if it is given by sum of y1 and y2. Okay. So then what we will do is we'll start with the derivation of the distribution function. So the cumulative distribution function, this is given by the probability of this capital variable, capital X less than some X. So then what is X? X is y1 plus y2. This is less than X. So then we have an integration of y1 and y2, uh, joint probability density function of y1 and y2. Then this is double integration, and then we have this condition based on this. Okay, and then how do we come from here to here? So let's go through that. So now let's say we have this y1 axis and this is my y2 axis. Now note that since y1 and y2 both are positive, so then we are only interested in the first quadrant. Okay, so we have x greater than y1 plus y2, or I can say y1 is less than y2 minus x, or x minus y2. Okay, okay, so then this means that, let's say this is my x. So what I'm trying to, so this is my x here. Okay, then I have to go like this. So this is my x here as well, because this one I can also say y2 is less than x minus y1. That's also the same thing. So then this is x here, this is x here. Okay, and our slope is -1 here because it's going like this. Okay, so then our limit of y1 is from 0 to, so this is my y2, so this is y1 is equal to x minus y2 line. So then this is my limit for y1, and my y2 limit is from 0 to, what is the maximum value? X here. So that's why you will see that what we did was, so this was the first one, the change of limits, and then we separated y1 and y2 PDFs because they are independent by definition, and then we plugged in the exponential distribution. So now then this guy is mu e to the minus mu y1, and then this guy is mu e to the minus mu y2. So that's why you have a mu squared here, and then that's why you have a y1 plus y2 here. Okay, and then we have mu squared here, and then what we did was, since the second second integral only has y1, so we separated out our e to the minus mu y2 here, and then we have this guy here. Now if we integrate this, we will get minus 1 over mu e to the minus mu y1. Okay, and then y1's limits will be from 0 to x minus 2, x minus y2. Okay, and then if we do that, if we open this, then we will get, the first term will be minus e to the minus mu x plus mu y2, and the second term will be minus 1 because e to the power of 0. Okay, and then we just repeated this here in the next page so that we have the clarity. Okay, and then if we simplify this, then we will see that this guy will be cancelled out with this guy, and then for the first term we will So this term is this term here, and the second term will be this one. And since we have a minus and minus both, so that's why I've written this one for this term here first. So then it e to the minus y mu y2 and then e to the minus mu x. Okay. Now then since uh, uh, these are separated by a minus sign, so we can separate the integral as well. So then we have an integral here and then we have an integral here. Okay. And then this guy again, this using the same approach. So from minus 1, this will become e to the minus mu x minus 1 and then divided by negative mu. And then this guy is just x because this is just 1 here. And then when we have a 1 here, we just subtract the upper limit from the lower limit. Okay. And then we are left with this expression here. Okay, and then if we simplify it again, so you will see that there will be some terms which will be cancelled again. So we will have um, uh, 1 here, and then we have e to the minus mu x. If we come here, then you will see that this is simplified as, so this one is actually this, this, and this. And this guy is this guy, and this guy is just this guy. Okay, so this is our actually CDF for our Erlang 2 distribution. Now what about the PDF? So we know that the PDF is just the differential of the CDF. So then what we do is what is the differential of this guy? This is not a 0. What is the differential of this guy? This is mu e to the minus mu x because of this mu. And then we have this guy here. So then we have the rules of the product of differentials here. So we'll keep this mu outside. Then first of all we keep x and and differentiate e to the minus mu x. So then we will get e to the minus mu x times minus mu, and then the second term we will keep e to the minus mu x and we differentiate x, and then we will get e to the minus mu x. Now if we do that, then you will see that this guy and this guy will be cancelled out, and we will only be left with mu squared x to the minus mu x, and then we can also add that x is greater than 0. Okay, so then all we did was we started with the CDF. We did some observation on the integrals where the right limits should be, and then we just kept on integrating with the knowledge we already have for once we until we have a simplified expression for the CDF. Once we had the CDF, what we did was we just differentiated it and then again simplified it to find the PDF. Okay, right. So hope it was easy to understand for Erlang 2 distributions probability density function. And thanks for watching. Hope you like the video.